Okay, great. So, hello everyone. My name is Battad. I'll be doing this talk today. I'm a grad student at the Cog Sci department at Rensselaer Polytechnic Institute, working with Dr. Macy. And I'd like to talk a bit about a system we've been building to understand image sequences using this idea of sense making and narrative. So, when bringing images, sequences of images to people and asking them to describe their contents or to write a story about them, what we find is that when explaining sets of images, human beings include a lot of information beyond what they see to tie things together. For example, this is a story that someone has written for this sequence of images. Jerry was riding through a field with his bike on his way to get some food. While he was in the restaurant, a few dogs came up to his bike. Jerry thought they were scary, so he called his friend Gertrude to help him scare the dogs away with her dog. And we could see some of the parts of these stories that are very firmly visually grounded, that there is a person, Jerry, ostensibly riding the bicycle that he was on top of, going through a field, that there are some dogs near that bike, etc. But there are a lot of details that aren't necessarily this visually grounded and are added to give these images a reason to be together. For example, the fact that he is on his way to get some food in the first image, and he's in a restaurant. So secretly in the second image, this person Jerry is off screen in a restaurant because he had that motivation to get some food. And the entire reason that the third image exists at all is because this new character, Gertrude, is Jerry's friend and has a motivation as well, is going to help scare the dogs away from the second image. What people identify when they're just looking for the visual facts in an image sequence like this are things like these, which aren't terribly interesting or surprising, but they're just visual facts like if there is a dog in a field, there are bicycles, there are people, etc. So our goal is to create a computational sense-making system that can create knowledge graphs from these sequences of images to support the sort of storytelling that we see in stories like this from sets of facts like these. To accomplish this, the task of the system is to interpret what's going on behind these images, and it needs to introduce a lot of new entities, events, evaluations, as well as connections between both new and old information. And furthermore, the information introduced has to be both relevant and non-conflicting. So to boil these down to sort of simplified system goals, it needs to bring in additional information, establish connections, and make sure those connections and that information is consistent. And the types of connections we're talking about are those found in narratives, specifically personal narratives, which are the closest sort of narrative to a person describing a set of images. Just zooming through these, the five categories of connections that we use are spatial, temporal, causal, referential, and affective, covering just the sorts of things that can tie together the base pieces of visual information that might be identified from these images. This is the overall architecture for the system that we have planned, although where we are focused on is the right side of this figure here, specifically the sense-making subsystem. So just going from visual observations to a knowledge graph. In lieu of some sort of computer vision system that can pull out these visual observations, we use scene graphs, human annotated scene graphs from the visual genome dataset, which gives us a large set of images with these scene graphs to work off of. And all these scene graphs tell us are what is physically or visibly on the images and any sort of visual connections that you can make between them. Someone is wearing something, something is near or behind something, etc. From these visual observations, the sense-making subsystem, which is the bulk of our current focus, then does a two-step hypothesis generation and evaluation process. The point of this is to pull in new information, add connections between that new information and the existing information in the scene graphs, and finally decide which of these hypothesized connections should be kept or rejected to maintain a sense of consistency. The sorts of knowledge graphs that the system creates looks something like this, where you have the base scene graphs in black and different sorts of hypotheses, such as what things are each other, which horses are the same horses across images, what events lead to or might be connected to each other, and what the emotions and motivations of different things in the images may be. For hypothesis generation, we draw from a large open source knowledge network called ConceptNet, which just gives us common sense knowledge. For example, that houses are places where kitchen tables are, etc. The sorts of hypotheses that the system generates are based on those narrative connections that I went over prior. For the current implementation, we focus on referential, causal, and effective relationships to show sort of the interconnection of information and some of the introduction of new information that these hypotheses can bring. Each hypothesis draws from one of three types of evidence: observational, which comes from visual attributes from the images themselves, aka the scene graph annotations; knowledge evidence, which comes from ConceptNet, our common sense knowledge source, and the system's own prior hypotheses, which it can draw from. And for an example, I'm going to go through an example of one type of hypothesis, the causal hypothesis, because it sort of wraps together all of these different types of evidence. So the hypothesis here is that the woman in the top image who is playing in that image has a causal sequence of events towards the woman in the bottom image who is identified as smiling in the annotations. From our prior knowledge from ConceptNet, there and the bottom purple chain of nodes, we have that both playing and smiling are concepts that have causal connections to having fun. So there is evidence that these two events are connected to each other. Further, from the system's own prior hypotheses, these two women have been identified as the same person or object or thing. There's a referential hypothesis between them, which adds the strength of that hypothesis to the strength of this causal hypothesis. And so the final hypothesis, that there is a sequence between playing and smiling, has the strength of the bottom path from the common sense knowledge source, and the strength of the prior hypothesis. With all of these hypotheses, with their own individual scores, the next step of hypothesis evaluation, which we cast as a multi-objective optimization problem, is the task of finding the combination of hypotheses which A, do not conflict, and which B, optimize a set of objective functions. The objective functions we use are two measures of graph topology, connectivity and density, and one measure of the strength of each hypothesis, which comes from the the hypothesis generation step. There are additionally some hard constraints on what hypotheses can be placed in the same set. The constraints we currently have implemented are both on the referential hypothesis, which basically say you can't say that the same existent appears in the same image twice, and you can't say that two things are each other and a third thing, which are both of them, is not both of those things. So the transitive property has to hold. And again, these are the sorts of knowledge graphs that this system produces. Currently, we are trying to evaluate the hypotheses that this version of implementation of this system creates. And there are several ways to do this. What we're focusing on are whether the elements of the system's output match the elements of human written stories. We are focusing on suspension of disbelief for visual differences, specifically for referential hypotheses, whether the things that humans in their human written stories say are each other match up with the things that the system's referential hypotheses say are each other. For example, that there is a same character, the pitcher or the batter, or same object, the ball, in human written stories and system generated hypotheses. All right, and I'll just leave us on the future work slide. Turkey done. Very good. And it's Slack that has any questions, right?
Yeah.
Right. Okay. I'll check there. I'll also have the Zoom chat open in case anybody wants to ask there.
Hey, Zev, this is Pat. I'm sorry I was not able to get into Slack, but I think this is a great problem. I encourage you to look at the sizable literatures on plan recognition and abductive inference because they're very relevant. And in particular, there's an old paper by Ng and Mooney, 1990, where they have a coherence metric for evaluating abductive explanations. It sounds similar to one of your criteria.
1990. Do you think you could type out the names of that paper?
I'll stick the reference in there.
All right, thank you very much.
They did not have explicit constraints. They had them, but they were sort of hidden. And look at my paper with Mohan to find out more about our stuff that's very related.
Yeah,
right.
In the Slack channel, there's a question wondering whether you had trouble with the noisy information from ConceptNet. I mean, it's kind of scattered what they show and what they represent and what they don't.
Right, we did. The largest problem we had are, because it's crowdsourced, people will call the same concepts different things. And we did need some way of collapsing those concepts as best we could. We looked to rooting of words for just an initial filter on things like that, but there is still noise. It is something that we are grappling with. I could talk to you about it more offline or through email if you'd like, Leilani Gilpin. So thank you for the question.
Are there people in your wider circle working on the left side of your master system diagram?
Yes, actually. So this project originally started in conjunction with another lab at RPI. They do a lot of image recognition and had a graduate student working on scene graph generation. So yes, the idea was to sort of have an interface between the two projects, and we would tackle the different areas there.